All right, in this video, we're going to talk about chapter 10 dealing with correlation and regression. We're only going to deal with the first two sections in this chapter. This first video will deal with correlation. The second video in chapter 10 deals with regression. All right, in section 10.1, correlation, we're going to be using paired data to find the value of the linear correlation coefficient, which is denoted by R, and then determine whether there is sufficient evidence to support a conclusion that there is a linear correlation between the two variables. Okay. So basically, in the textbook, there are like two parts, but we're just going to deal with just part one for now. That deals with some of the basic concepts of correlation. And then also we'll look at how to do a hypothesis test for a correlation between two variables. Okay, so let's start off with some definitions here. A correlation exists between two variables when the values of one variable are somehow associated with values of the other variable. Okay. It's just an association between two variables. Now, linear correlation, more specifically, that exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. Okay, so here's a couple of examples here, or a couple of illustrations that I have here dealing with correlation. The one on the left is a positive correlation. As you can see, these points are rising from left to right. So there is a positive correlation between two variables, X and Y. So in other words, as X increases, Y increases. Now, the one on the right is a negative correlation. You can see that these points are declining or falling from left to right. So in other words, as your X values increases, your Y values are going to be decreasing. Okay. And notice the R for each one of those correlations here. For a positive correlation, they came up with R is equal to 0.851. And for negative correlation, their R value was negative 0.965. Okay, another illustration is this. This one has no correlation. As you can see, the points are all over the place. Here, there's no pattern, no straight line pattern. Now, for part D, we have what they call a nonlinear relationship. Okay, notice that these points, it's not in a straight line pattern, but it does have a distinct pattern. And some textbooks call this a curvilinear relationship. Okay. So some textbooks call this curvilinear. Because the points form a curve, but it doesn't form a straight line pattern. Okay. All right, now let's look at another definition. Now, those R's that we just saw, those R values that we talked about, that's what we call the linear correlation coefficient. It measures the strength of the linear correlation between the paired quantitative X and Y values in the sample. Okay. And the linear correlation coefficient is sometimes referred to as the Pearson product moment correlation coefficient. And that's in honor of Karl Pearson, who originally developed it. Okay. Now, because the linear correlation coefficient is calculated using sample data, it is a sample statistic used to measure the strength of a linear correlation between X and Y. Now, if we had every pair of XY values from an entire population, then in this case, we will have a population parameter which is represented by the Greek letter rho. Okay. So that linear correlation coefficient, if we were dealing with a population, it would be the Greek letter rho. But for a sample, it would be lowercase r. Okay. So now let's try to find the linear correlation coefficient. And these are just some notations here. Lowercase n is just the number of pairs of sample data. Keep that in mind. Number of pairs, not the individual data values, the number of paired sample data. Sigma is the addition of the items indicated. Sigma of x is the sum of all x values. Sigma of x squared will be that each x value should be squared, and then those squares will be added. And then this notation, the sum of your x's and then u squared, that indicates that the x value should be added, and then the total will be squared. Okay. So do not get these two notations confused. This one, we square the x's and take the sum. This one, we square the x's, and then that total will be squared. And more notation, the sum of x, y, that means each x value should be multiplied by its corresponding y value, and after obtaining those products, we're going to find the sum. And of course, R is a linear correlation coefficient for the sample data, and rho is a linear correlation coefficient for a population of paired data. Now, here's some requirements. There are 3 of them. One of them is that the sample paired XY data is a simple random sample of quantitative data. In other words, what we mean by simple random sample, samples of the same size have an equal chance of being selected. That's what that means. Number 2, visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Now, we're going to be doing scatter plots here shortly, how to construct a scatter plot. But if you're not familiar with what a scatter plot is, of course, these are what scatter plots look like, because this is what we use to measure, to visualize the relationship between 2 variables in this case. So we use a scatter plot. Okay, and number 3, because results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without outliers included. Okay. Now, here's a couple of formulas for calculating R. The one we're going to use, well, I just introduced these because more than likely we're not going to be using that formula. By looking at it, it might seem a little bit complicated. Formula 10-1, it says R is equal to N times the sum of the X times Y minus the sum of the X times the sum of the Y. All that's divided by, and in the denominator, you have 2 square roots. One would be on the left side, the square root of N times the sum of your X squares minus the sum of the X's and it squared, times another square root of N times the sum of the Y squares minus the square of the sum of all your Y's. Here, this simplifies manual calculations, but R is usually calculated with computer software or a calculator. More than likely, we're going to be using the TI-83 or the 84 plus calculator to come up with our R value. All right, now the other formula says R is equal to the sum of z sub x times z sub y, all divided by n minus 1. Now, they use this formula to better understand the reasoning behind R, where z of x denotes the z-score for an individual sample value x, and zy is the z-score for the corresponding sample value y. But in this video, we're just going to be using the TI-83 or the 84 plus calculator, so you won't have to memorize that particular formula. Now, how can we interpret the linear correlation coefficient R? If we're using computer software to interpret this, here we want to find if the p-value computed for R is less than or equal to your significance level. If that's true, we can conclude that there is sufficient evidence to support the claim of a linear correlation. Otherwise, there's not sufficient evidence to support the claim of a linear correlation. What that means here is if your p-value is greater than your level of significance. Now, on the TI-83 and 84 plus calculator, you'll be given the R value as well, and the p-value. That way you can get the p-value, use that to compare that with your level of significance. We can also use table A-6 to interpret R. And if you're not familiar with table A-6, it should be at the last page of your handout. And this is what table A-6 is. Those are the critical values of the Pearson correlation coefficient R. You'll look for n, which is the number of paired data, and your alpha level, we're only going to be using either 0.05 or 0.01. And that's it. And that will read across and down, you'll get your critical Pearson correlation coefficient, the critical value. So in this case here, sometimes it just have to draw a graph. Now, keep in mind the critical values are going to be both positive and negative. So let's say here, if I had 6 paired data, my alpha level was 0.01, then my critical value here would be plus or minus 0.917. That means I'll have negative 0.917 and positive 0.917. Now, if the computed linear correlation coefficient R lies in the left tail beyond the leftmost critical value, or if it lies in the right tail beyond the rightmost critical value, then we can conclude that there is sufficient evidence to support the claim of a linear correlation. However, if the computed linear correlation coefficient lies between the two critical values, then we can conclude that there is not sufficient evidence to support the claim of a linear correlation. Now, on the next page, there is an equivalent criteria. Here they deal with absolute value of R, which is this. If the absolute value of R exceeds the value in table A-6, then we can conclude that there is a linear correlation. Otherwise, there's not sufficient evidence to support the conclusion of a linear correlation. Okay. Also, the round-off rule is to round the linear correlation coefficient R to 3 decimal places so that the values can be directly compared to your critical values in table A-6. So now, if you're manually calculating R and other statistics, you want to round in the middle of the calculation. Rounding in the middle of the calculation often creates substantial errors. So you want to wait until the final result to round off your R values to 3 decimal places. Okay, because you want to get an accurate linear correlation coefficient R. Now here's some properties of the linear correlation coefficient. One is that the value of R is always going to be between -1 and 1 inclusive. That means that R value will never be less than -1. It will never be greater than +1. Has to be between -1 and 1. And that does include those two endpoints. Number two, all the values of either variable are converted to a different scale. The value of R, if all the values of either variable are converted to a different scale, the value of R does not change. And then number three, if the value of R is not affected by the choice of X and Y, interchange all X and Y values and the value of R will not change. And then number four, R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. And R is very sensitive to outliers in the sense that a single outlier can dramatically affect its value. So you want to be careful of that. Okay. Next, we'll talk about explained variation. The value of R squared. So when you find R and you square it, you're going to get what they call the explained variation. And R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. Okay. Now, there are some common errors that are related to correlation, that involve correlation. Number one, assume that correlation implies causality. That's one big error because you might have a correlation between the two variables, but we can't say that one is the cause of the other. You can't say, like smoking and lung cancer, we can't say that smoking causes lung cancer. Number two, data based on averages is another common error. And of course, property of linearity is also another common error. So at times you want to avoid these errors if at all possible. All right, the second part is the formal hypothesis test. In this case here, N is the number of paired data, R is the linear correlation coefficient for the sample paired data, and rho is the linear correlation for a population of paired data. Okay. Now, in the hypothesis test for linear correlation, there are requirements. They're the same as those given for determining a linear correlation between the two variables. Okay. Now, our hypothesis is always going to be this. The null hypothesis will always be rho is equal to 0, meaning that there is no linear correlation between the two. And your alternative hypothesis, H1, will be rho is not equal to 0. It's always going to be like this. Rho not equal to 0 means that there is a linear correlation between the two variables. Okay. Your test statistics is always going to be R, which you can obtain from technology. We'll be using TI 83 and 84 plus calculator. The critical value you get from table A-6. And also, sometimes they may ask for the p-value. The p-value can be obtained by using your TI 83 or 84 plus calculator. All right, and your conclusions are, of course, if the computed linear correlation coefficient lies in the left tail beyond the leftmost critical value, or if it lies in the right tail beyond the rightmost critical value, you reject the null. Or if the absolute value of your linear correlation coefficient is greater than whatever that critical value is, you reject the null hypothesis. Otherwise, fail to reject the null hypothesis. And that's also indicated down here in this case. Now, of course, the p-value method, of course, you compare your p-value with your level of significance. And if that p-value is greater than your level of significance, you reject the null. Otherwise, fail to reject the null hypothesis. And as you can see here, this is pretty much the same that I just mentioned. But here, the test statistic, if you were using a t-test, it would be this. Okay. But again, we're using the TI 83 or 84 plus calculator for all of that. Okay. Now, this rarely happens, but in a one-tailed test, it can occur with the claim of a positive linear correlation or the claim of a negative linear correlation. And these are the null and alternative hypotheses that are related to that. But in these examples that we'll be doing in this video, this rarely happens. You won't be seeing those. Okay. And I'm using the critical value method for the procedure for testing a hypothesis. Okay. And that's this: you state the original claim, then state the opposite of the original claim, and then identify the null and alternative hypothesis. Those should be easy because the original claim would be rho is not equal to 0, meaning that there is a linear correlation. The opposite would be rho is equal to 0, meaning that there is no linear correlation. And of course, your null hypothesis will be rho is equal to 0. Your alternative hypothesis will be rho is not equal to 0. And that will also be the claim. State the level of significance that will be given to you in the examples. Compute the test statistic R using your TI 83 or 84 plus calculator. You'll use table A-6 to identify your critical value. And then if the absolute value of R is greater than the critical value, you reject the null. Or if the absolute value of R is less than or equal to your critical value, fail to reject the null hypothesis. And of course, we write the conclusion using simple non-technical terms. And I've also included some the procedure for entering a list of data using the TI 83 and 84 plus calculator. And for constructing a diagram. And of course, we'll talk about the linear regression t-test, okay? And we're gonna have to use that in this video because I have yet to find another way to get the R value other than using the linear regression t-test, okay? We'll talk about these as we do some of these examples here and how to enter data into the TI 83 or 84 plus calculator. Okay, but you'll use that to help you do this. All right, let's start with example 1, where we got 54 wild bears were anesthetized, and their weights and chest sizes were measured and listed in a data set. Results are shown in the accompanying data display, as you can see. Is there sufficient evidence to support the claim that there is a linear correlation between the weights of bears and their chest sizes? When measuring an anesthetized bear, is it easier to measure the chest size than weight? If so, does it appear that a measured chest size can be used to predict the weight? Use a significance level of alpha is equal to 0.05. So here's our display right here on the right side. And we're going to go through that 8-step procedure, okay? So of course, in step number 1, we always write the original claim in symbolic form. And that's going to be rho is we want to determine if there is a linear correlation. So that would have to be, of course, not equal to 0. Because if you look back at those notes, you'll see that rho not equal to 0 means that there is a linear correlation. Step number 2 is the opposite of the original claim. Well, the opposite of not equal to would be just plain equal to. So it'd be rho is equal to 0. And then step number 3 is identifying the null and alternative hypothesis. Well, of course, the null always has the equal sign in it. So the opposite of the original claim must be the null. And then your original claim, rho is not equal to 0, is the alternative. And I'm going to write the word claim here. And pretty much in these examples, step 1, step 2, and step 3 are going to be the same. It's always going to be like that because you're testing the claim whether if there is a linear correlation between two variables. And then step number 4 is your level of significance. You're told to use a 0.05 level of significance that's given to you in the problem. Step number 5 is our test statistic, which is, of course, R. So pretty much we can identify R, which is your correlation coefficient R. That's this value, 0.95409. But to 3 decimal places, this will be 0.954. So 0.954 is your test statistic. And then step number 6 is the critical value. Here's your critical value right here. And that's going to be plus or minus. And I want to round this off to 3 decimal places. This will be 0.268. 0.268. And now step number 7. I'm going to use this decision rule here. If the absolute value of R is greater than the critical value, reject the null hypothesis. Okay, now here's what I'm going to do here. Take the absolute value of R, which is 0.954. Now keep in mind the absolute value is always going to be positive. It will never be negative. So the absolute value of 0.954 is 0.954. And I'm going to take the positive value of my critical value, which is 0.268. And as you compare those two, you're going to see that 0.954 is greater than 0.268. So that means I need to reject the null hypothesis. Reject the null hypothesis. And then finally, step number 8 is to write my conclusion using simple non-technical terms. If I reject the null, and of course, the claim was the alternative, that means that there is sufficient evidence to support the claim that there is a linear correlation between the weights of bears and the chest sizes. Okay. Now, in this example, there are other parts of the question where it says that when measuring an anesthetized bear, is it easier to measure chest size than weight? And if so, does it appear that a measured chest size could be used to predict the weight? And in this case, that answer would be yes. Okay. Okay, because it is easier. Well, it is easier to measure the chest size than weight. It is easier to measure chest size than weight. Okay. Because the fact you have to lift the bear up to on the scale to even weigh it. So that takes time. So just measuring that chest size would be easier. And also, since there is a linear correlation between the weights of the bears and the chest sizes, the chest size can be used chest size can, let me erase this. Can be used to predict weight. Okay. All right, so that's example 1 and how that is done using the 8-step procedure. All right, now let's take a look at example 2. Here's another display given to us, a little bit different from the first one. A data set includes weights of garbage discarded in 1 week from 62 different households. The paired weights of paper and glass were used to obtain the results shown here at the bottom. Is there sufficient evidence to support the claim that there is a linear correlation between weights of discarded paper and glass? Use a significance level of alpha equal 0.05. Okay. So if we were to go through that 8-step procedure, then step number 1, which is your original claim, that's of course rho is not equal to 0, meaning that there is a linear correlation between the two. Step number 2 is the opposite. Rho equal to 0 means that there is no linear correlation. And then step number 3 is the statement of the null and alternative hypothesis. That means rho is equal to 0 and rho is not equal to 0. And rho not equal to 0, the alternative hypothesis is the claim. And it's always going to be like this when you're dealing with a linear correlation between two variables. Step number 4 is the level of significance, 0.05. And then step number 5, we're looking at the linear correlation coefficient R. Well, they're both right here, 0.1830. To 3 decimal places, this will be 0.183. Now, step number 6, we're going to need the critical value for this. Okay. What I see here is this. I see 62 different households, so that tells me N is going to be 62. And my alpha level is 0.05. So here I'm going to use table A-6 to find out what my critical values are. Well, let's just say critical value. Now, here's table A-6. Now, you're not going to find 62 in the table. Well, let's use a value closest to 62. I'm going to use 60. And the level of significance, I'm either going to use 0.05 or 0.01. I have 0.05 significance level here. So let's use this first column, 0.05, and I'm going to use 60. And this will be my critical value, 0.254. So the critical value here would be 0.254. That's my critical value. And now step 7 is my decision rule. And if you look at table A-6, you're going to see what that decision rule is. Reject the null hypothesis if the absolute value of R is greater than the critical value in the table. So let's use that. So I'm going to say here, if the absolute value of R is greater than the critical value from table A-6, reject the null hypothesis. So if I take the absolute value of R, and R was 0.183, again, the absolute value is always going to be positive. That would be 0.183. Now compare that to the 0.254. If you compare those two, 0.183 is less than 0.254. Less than 0.254. It violates the decision rule, so I need to fail to reject the null hypothesis. Fail to reject the null hypothesis. And then step number 8 is this, writing the decision rule, the conclusion. Here we failed to reject the null hypothesis. The claim was the alternative hypothesis. So that means that there's not sufficient evidence to support the claim. There is not sufficient evidence to support the claim. that there is a linear correlation between weights of discarded paper and glass. Now, those first two examples were quite easy because you already had the display from some type of software that they use to get the output. Now, let's say we had the raw data, like in example 3. Here we're going to use the given data to complete parts A through C below and use the alpha level equal to 0.05. So here we've got raw data for X and Y. We've got paired data. Now in part A, you're to construct a scatter plot. All right, so here's where we use our TI-8384 plus calculator to construct the scatter plot. And also, that's where we use this particular handout. Okay. Not only to enter the list of data values here, but also to construct the scatter diagram for this. Okay. So let's start by turning this on, clear this out. In this case here, to enter this raw data, we have to first press the stat key. Here's the stat key, we press that. We're entering in new data, so edit is highlighted and we select number 1 for edit. Now notice I got stuck in here. To clear this out, what I'm going to do is use my up arrow key to highlight the L1 or L2, and then press clear and then enter. Close it out. And then for the other list, highlight that. Here I'm highlighting L1 in this case, using the up arrow key, and then clear, enter. That clears out all that data. So now I'm going to be entering in L1 the X values, and L2 I'm going to enter the Y values. So my X values will go into L1. So in this case, I'm going to type in the 10 and then enter. And you have to press enter after each data value, even the last one. So you have 10, 8, 13, 9, 11, 14, 6, 4, 12, 7, and 5. Then I use my right arrow key to go to L2 and enter the Y values here. And in this case, it's going to be 9.14, and then 8.15, 8.73, 8.78, 9.25, 8.11, 6.14, 3.11, 9.14, 7.25, and 4.73. All right, now it is very important that the same number of data values you have in L1 has to be the same number of data values in L2. If they're not, then you need to look over your data value, see if you missed any one of those, and make sure that your data values are correct as well. Now to construct this scatter diagram, now that we have the data values in, we've already done number 1 and number 2. Now you're going to select stat plot, the stat plot function by pressing second and y equal to. Okay, so from here we can do this. Press the second key, which is this blue key, and then the y equal to is at the very top of the calculator. Now I do need to mention something. We're going to select number 1 for plot 1. I do need to mention this right here. If your plots are off, if off is highlighted, you want them on. So to do that, use your left arrow key, put the cursor on, and press enter because you want the stat plot to be on, or your plots to be on. Under the next line, you'll see type. Make sure that this first one is highlighted because that's the one we want, a stat plot. So here you use your down arrow key and then press enter to make sure that's on. Your X list should be L1. If it is not, what you need to do there is press second and the number 1 key for L1. And your Y list should be L2. Press second and L2 if you don't see an L2 there. Okay, X list should also always be L1, Y list should always be L2. The mark for your points on the graph, it could be one of these 3. I choose the first one for that one. Okay. But the other 3 are up to you if you like. Okay. Now, don't worry about the color. I mean, it could be whatever you like, but don't worry about that. But finally, you're going to do this right here. To obtain the scatter plot, you have to press the zoom and number 9. The zoom is this button at the very top. Press zoom. And then you're going to select menu item number 9, which is zoom stat. So you can use your down arrow key or press the number 9 key for zoom stat. And this is what the graph should look like for this. And you can see here it does have a distinct pattern, but it's not in a straight line pattern just by looking at it. So this right here was part A, just constructing the scatter plot. Now in the homework, you'll be given a choice of scatter plots. You just want to pick the scatter plot that is close to the one that you have here. I want to mention that. But that's how you construct a scatter plot using a graphing calculator, mainly the TI-83 or 84 plus. Okay, so I'm just going to say here in part A, use the TI-84 plus calculator. Part B is finding the linear correlation coefficient R, then determine whether there is sufficient evidence to support the claim of a linear correlation between the 2 variables. Okay, so that's where we use that 8-step procedure for hypothesis testing. So here's step number 1 is the original claim. The claim is that there is sufficient evidence, well, to support the claim of a linear correlation between the 2. So it has to be rho is not equal to 0, meaning that there is a linear correlation. That's our claim. Step number 2 is the opposite of the claim. That rho is rho is equal to 0, meaning that there is no linear correlation. Rho is equal to 0. And then step number 3 is the null and the alternative hypothesis. The null always has the equal sign, rho is equal to 0, but the alternative has the not equal to sign. And our alternative is always going to be the claim. And again, this is always going to be that way when you're dealing with a hypothesis test for a linear correlation. All right, step number 4 is your level of significance. And that's, of course, alpha is equal to 0.05. That is indicated in the example. At the very top tells you to use a 0.05 level of significance. All right, now step 5 is going to be that linear correlation coefficient, which is your test statistic. So we can get that from the TI 84 plus calculator. Here's how we're going to do that. Let me turn this back on. Now, let's press the stat key. No, stat key. Use your right arrow key to highlight test. Now, the menu item for that, and you're going to have to use your down arrow key to find this one. It's called LinReg t-test. It's called the linear regression t-test. And we're going to talk about that when we get into section 10-2, dealing with regression. But for now, we're going to use LinReg t-test. Now press enter. XList is going to be L1. Again, you have to do second and then number 1 for L1 for your XList. And then for L2, that's your Y list. You have to do second L2 for L2 to show up. That's going to be your Y list there. Frequency is going to remain at 1. This is beta and rho in Greek letters. Not equal to 0 will always be highlighted. You're never going to have to use less than 0 or greater than 0. You'll be using not equal to 0, and that's going to come from your alternative hypothesis here, where rho is not equal to 0. Okay, skip over this and then go down to calculate. Put the cursor on calculate, press enter. Okay. Now you'll get this, but notice that arrow down the bottom. That means that there's more stuff on here. So you're gonna have to use your down arrow key all the way down to get the value of R, which is what you'll see right here, 0.816. If you were to round it to 3 decimal places. So that's your linear correlation linear correlation coefficient. 0.816. All right, now step number 6. Now, unless otherwise indicated, I would suggest using the critical value if at all possible. But if they ask for the p-value, you can get that straight from the calculator. Now I need to move back up. So here's that p-value right there, 0.002. But in this case, in this example, I'm going to get the critical value. N is 11. Notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 paired data. And the alpha level is 0.05 as indicated. So if I use table A-6 to get my critical value, the critical value from table A-6, which is this right here, I have 11 paired data. The alpha level was 0.05. Read across and down, you'll see that the critical value there will be 0.602. 0.602 is your critical value. And now step number 7 will be your decision rule. And that's going to be this. If the absolute value of R is greater than the critical value from table A-6, we can reject the null hypothesis. And in this case, if I take the absolute value of R, which was 0.816, that's going to be 0.816 anyway. The critical value was 0.602. Compare 0.816 to 0.602. You'll see that it is greater than your critical value. It does satisfy the decision rule. So that means we need to reject the null hypothesis. Reject the null hypothesis. And then step number 8 is writing our conclusion statement using simple non-technical terms here. The claim was the alternative hypothesis. We rejected the null. That means that we have sufficient evidence to support the claim. So that means that there is sufficient evidence to support the claim that there is a linear correlation between the two variables, x and y. Okay. Now in part C, they ask us to identify the feature of the data that would be missed if part B was completed without constructing the scatter plot. Okay. Now I'm gonna bring this back up because I want to show you something here. I'm gonna do zoom 9 to bring back up this graph of the scatter plot, as you can see here. Had we not done this, we would have missed out on this showing that it does have a distinct pattern that is not a straight line pattern. As you can see here, it's like a curve here. So in this case here, this is not a straight line pattern. So to answer that question, the scatter plot reveals a pattern, a distinct pattern that is not a straight line pattern. Okay. All right, so that answers example 3. Now, notice in steps 6 and 7, I used the critical value. I could have used the p-value if I wanted to. Let me show you what I mean here. Okay. I could have used the p-value right here because this does gives me the p-value. And this p-value would have been 0.002. And I can compare that p-value with this level of significance of 0.05 and easily rejected the null because the p-value is less than your level of significance. So we can reject the null and come up with that same conclusion for step number 8. that there is sufficient evidence to support the claim that there is a linear correlation between the two variables. So here you can use either the p-value approach or the critical value approach and still come up with the same conclusion of rejecting the null. Okay, look at example 4. It says here listed below are numbers of internet users per 100 people and numbers of scientific award winners per 10 million people for different countries. Construct the scatter plot and find the value of the linear correlation coefficient R and find the p-value of R. Determine whether there is sufficient evidence to support the claim of a linear correlation between the two variables, and use a significance level of alpha is equal to 0.01. Okay. So now, for the scatter plot, we're going to use the TI-83 or 84 plus calculator. Now I'm just saying TI-84 plus calculator because I don't know of many TI-83 calculators that are floating around. With technology these days. Okay. So let's clear this out. Let's go to stack, press the stack key. We're putting in a brand new table, so we need to edit. I select the number 1 and clear L1 and L2. Up arrow to highlight L1, press clear, enter. Right arrow over to L2, up arrow to highlight L2, press clear, enter. And now we're going to enter the numbers for internet users in L1 and the numbers for award winners in L2. So let's start with the internet users. That row will be in L1. So that's 78.4. Oops. Need to. Okay. Go back to L1. Now 78.4 is going to be in L1, and then 80.1, 56.4, 66.6, 76.7, 38.5. And then hit your right L key. Award winners will go into L2, 5.4, 8.6, 3.3, 1.8, 10.4, 0.1. Okay, make sure you hit enter after each data value, including the last one. And make sure that your data values are correct. And also you have the same number of data values in L1 as you do for L2. Okay. So now we're going to do second and then y equal to for our scatter plot. And then we're going to select number 1. Plot should still be on. The first icon that you see there should be highlighted for the type. L1 should be in X list. L2 should be in the Y list. The mark can be whatever you like. I'm choosing the first one. Okay. So once all that's taken care of, you do zoom and then go down to number 9 if you want to, or you can press the number 9 key, then enter. And this is what the graph looks like. Again, in the homework, you'll be given a choice of graphs to use to select. You'll select the one that's close to the one that you have on your screen in the calculator. Okay. All right, now step number 1, we're going to start our hypothesis testing. Step number 1, you want to state the original claim using in symbolic form. Not form, original claim. So that's going to be rho is not equal to 0, meaning that there is a linear correlation between the two variables. And then step number 2 is the opposite of the original claim. That's rho is equal to 0. And then step number 3 is stating the null and the alternative hypothesis. Of course, the null always has the equal sign, and the alternative has the not equal to, and that's also the claim. And then step number 4 is your level of significance. This time is 0.01. All right, and then step number 5 is this. I'm going to use the TI-84 plus calculator to get my linear correlation coefficient, which is the test statistic. All right, so to do that, I'm going to press the Stat key, use my right arrow key to highlight test, go all the way down to linreg t-test. Linreg t-test. And then press enter. All right, XList should be L1, while this should be L2, not equal to should be highlighted. So we go all the way down to calculate, and then press enter. Use your down arrow key to find R. And R in this case to 3 decimal places will be 0.813. Because as you can see, the third digit is a 2. The 7 makes that 2 or 3. Round it up. So that is your linear correlation coefficient. That's going to be your test statistic. All right, now in step number 6, let's say I want to find the p-value instead of the critical value. That can be obtained from the TI-84 plus calculator as well. And here it is. And I'm going to use my up arrow key to go all the way up to the top. The T is there. Here's your p-value right underneath it. So if I was to round this off to, let's say, 3 decimal places, that would be 0.049. 0.049. That would be the p-value, okay? But if they ask for the critical value, then that means you have to look at the number of paired data here, which is in this case, there are 6 paired data, and your alpha level of 0.01. And you have to use table A-6 to get that critical value, okay? But here we're finding the p-value. So in step number 7, we have to compare the p-value with our level of significance here to determine whether we need to reject the null or fail to reject the null. So in this case here, if your p-value is less than or equal to alpha, reject the null hypothesis. Otherwise, fail to reject the null hypothesis. Your p-value is 0.049. The alpha level is 0.01 from step number 4. And if you compare the two, you're going to see that 0.049 is greater than 0.010. this does not satisfy the decision rule, so that means I need to fail to reject the null hypothesis. Fail to reject the null hypothesis. And then step number 8 is our conclusion. Well, we failed to reject the null and the claim was the alternative. That means that there's not sufficient evidence to support the claim. So in detail, there is not sufficient evidence to support the claim. That there is a linear correlation between internet users and award winners. Okay. All right, now let's look at example 5. And this is the last example in this video, by the way. Police sometimes measure shoe prints at crime scenes so that they can learn something about criminals. Listed below are shoe print lengths, foot lengths, and heights of males. Construct a scatter plot to find the value of the linear correlation coefficient R and find the p-value of R. So they're asking for the p-value in this problem here, just like they did in the last example. Determine whether there is sufficient evidence to support the claim of a linear correlation between the two variables. Based on these results, does it appear that police can use shoe print lengths to estimate the height of a male? Okay, so they're looking at shoe print lengths and height of a male. Now, in this problem, they're giving you the shoe print, foot length, and height, but we're looking at a correlation between shoe print and just the height. So I'm going to cross out this middle row of foot length, okay? Sometimes they give you additional information that you're not going to need in order to answer the question. And in this case, we're only going to be concerned with shoe print length and height of a male, just those two. And now let's do the scatter plot. Of course, we're going to use the TI-83 /84 plus calculator, depending upon which calculator you have. I'm using the 84 in this video. And we only are going to be concerned with the shoe print and height. So shoe print will go into L1 and height will go into L2. In this case, let's clear this out. Press the stat key. We're going to edit. We'll put in new data. So we select number 1 for edit. Let's clear L1 by using the up arrow key to highlight L1, then clear, and then enter. Go to L2, use the up arrow key to highlight L2, press clear, and then enter. I'm gonna go back to L1 where I will enter the shoe print in centimeters. So here I get 29.8. Enter that, and then 29.8 again, 32.3, 32.5, 27.6. And then use my right arrow key to go to L2. L2 will be the height in centimeters. So this is 173.5, 170.8, 181.2, 177.5, 167.8. Okay. Make sure your data values are correct, and also make sure that you have the same number of data values in L1 as you do in L2. Okay. I'm gonna put this off to the side. Well, no, I don't. I need the scatter plot, of course. Sorry about that. All right, so to get that, we go to second and y equal 2. And select number 1, because the plots are already on. And also, this first icon is selected for the scatter plot. X list is L1, Y list is L2. The mark could be whatever you want to. After that, go to press zoom, go all the way down to number 9, and press enter. That's what the scatter plot looks like. And in the homework again, you'll be given a choice of scatter plots. You want to select the one that is closest to this one that's in the screen. Okay, so now let's do our 8-step procedure to determine whether we have a linear correlation between the two. These two variables, shoe print and height. So step number 1 is the original claim in symbolic form. In this case here, rho is not equal to 0, meaning that there is a linear correlation. That's our claim. Step number 2 is the opposite of the original claim. And that's, of course, rho is equal to 0, meaning that there is no linear correlation between shoe print and height. Step number 3 is writing the null and our alternative hypothesis. And of course, the null always has equal sign. The alternative does not, has the not equal to. That's also the claim. So again, step number 1, 2, and 3, that's all, it's always like that. Okay. Step number 4 is your level of significance. Here the alpha level is 0.01. And now step number 5, that's where we use the TI 84 plus calculator. Which is what I'm using. You might use the TI 83. To get your linear correlation coefficient, which is R. So in this case, I'm going to press the stat key, go over to test using the right arrow key, use the down arrow key to find linreg t-test. Press enter. L1 should be in the X list, while it should have L2, frequency is still going to be 1, not equal to should still be highlighted based on the alternative hypothesis, not equal to. So we can use our down arrow key all the way down to calculate, then press enter. Use the down arrow key to find out what R is. There's your R right there. So 3 decimal places, this will be 0.939. Now I'm gonna also add something else, what t is equal to. In the homework, they may ask for what t is equal to. You can get that from this calculator here, because if you use your up arrow key, go all the way back up. Here's what t is equal to. And let's say I want to round this off to 2 decimal places. That means your t will be 4.71. That's your t value. That's your t-test statistic, I should say, 4.71. Okay, and now step number 6 is again, we're going to use the TI-84 plus calculator to get our p-value, because that's what they asked for in this case. And of course, the p-value can be taken from this from the screen right here. Here's your p-value. Let's see, the 3 decimal places, this will be 0.018. Okay. So that's your p-value, 0.018. Now we're going to compare the p-value with our level of significance here. So in step number 7, the decision rule is this. If the p-value is less than or equal to your level of significance, or alpha, reject the null hypothesis. And here the p-value is 0.018. The alpha level is 0.01. Compare those two, you'll see that 0.018 is greater than 0.01. Does not satisfy the decision rule, so that means we need to fail to reject the null hypothesis. Fail to reject the null hypothesis. And then finally, step number 8 is our conclusion. We failed to reject the null hypothesis, but the claim was the alternative hypothesis. That means that there's not sufficient evidence to support the claim. So here, there is not sufficient evidence to support the claim that there is a linear correlation between shoe print lengths and heights of males. Okay, that's the 8-step hypothesis testing procedure. And they ask, based on these results, does it appear that police can use shoe print lengths to estimate the height of a male? And the answer there will have to be no. And that's because of course, shoe print length and height do not appear to be correlated. Okay. They do not appear to be correlated. Okay. Unfortunately, I made a mistake. I have one more example to give you. We'll look at this one right here. Listed below are the overhead widths in centimeters of seals measured from photographs and the weights in kilograms of the seals. Construct a scatter plot and then find the value of the linear correlation coefficient R and find the critical values of R using alpha is equal to 0.05. Is there sufficient evidence to conclude that there is a linear correlation between overhead widths of seals from photographs and the widths of the weights of the seals? And here's that table. Okay. So in the past two examples, we were using the p-value, finding the p-value. Now they want the critical value. So we have to use table A-6. But first we need to do the scatter plot. By using the TI 84 plus calculator. I just mentioned that. Okay, so in this case here, let's press the stat key. We have to select number 1 to edit because we're putting in brand new data. To clear this out, highlight L1 using the up arrow key, clear, and then enter. Go to L2, use your up arrow key to highlight L2, press clear, and then enter. So overhead width will go into L1, the weight goes into L2. So for the overhead width, we got these data values: 7.1, 7.6, 9.8, 9.3, 8.8, and 8.4. Use your right arrow key to go into L2. Your weight, we enter those in individually: 115, 187, 249, 199, 201, and 192. Okay, there we have it. So now we're going to go to second, let's see, second, y equal to. Select number 1 to plot. Plot should be on. The first one should be highlighted for the type, which is a scatter diagram. L1 should be for X-list, and L2 should be for the Y-list. The mark should be, well, it can be whatever you want. And then we're going to press the zoom key and then press number 9. And that is what your scatter plot should look like. And then the homework, you just select the one that fits the one that you see here. Okay, so now let's go ahead and do our 8-step procedure. So in step number 1 is the original claim in symbolic form. That's, of course, rho is not equal to 0, because that's just saying that there is a linear correlation between these two. Step number 2 is the opposite of the original claim. The opposite of not equal to is equal to, so rho is equal to 0. And then step number 3 would be the null and the alternative hypothesis. The null always has the equal to sign in it, so it'll be rho is equal to 0. The alternative has not equal to, so rho is not equal to 0, and it is also the claim. And then step number 4, alpha level is 0.05, because it says use a 0.05 level of significance that's given to us. All right, so now we're going to use our TI-84 plus calculator. or 83. To find our linear correlation coefficient, or in this case, R. So here we go. To do that, we press the Stat key, right arrow to test, down arrow key to go down to LinReg t-test. Excuse me. And then press enter. X-list should still be L1, while this should still be L2. Frequency is still going to be 1, not equal to 0 should always be highlighted based on the alternative hypothesis. Go down to calculate and then press enter. And use your down arrow key to find out what R is. To 3 decimal places, that would be 0.844. So that is your linear correlation coefficient, or your test statistic. So now step number 6. Now in the problem, it does say find the critical values of R. Here we go. I'm using table A-6, and N is 6, because there are 6 paired data values. 6 paired data. And the alpha level is 0.05. This means we want our critical values, and there are 2 of them. One's excuse me, one's positive and the other one is negative. So here's table A-6. Your N is 6, your alpha level is 0.05. So that means if you go across and down, you'll see the critical value 0.811. And there are 2 of them, by the way. One's negative, so there's negative 0.811. And the other one is positive 0.811. So you got 2 critical values here. And now step number 7 is our decision rule. And I'm using the decision rule that is given in table A-6. And that's this. If the absolute value of R is greater than the critical value in the table, reject the null hypothesis. So if the absolute value of R is greater than the critical value in table A-6, and I'm using a positive critical value here, reject the null hypothesis. If I take the absolute value of R, which was 0.844, I would get 0.844. Because keep in mind, absolute value is always going to be a positive number. The critical value is 0.811. And I'm using the 0.811 that was given in table A-6. Compare those two, you'll see 0.844 is greater than 0.811. It does satisfy the decision rule, so that means I need to reject the null hypothesis. And if I reject the null hypothesis, the claim was the alternative, that means I have sufficient evidence to support the claim. So in step number 8, my statement will be this, that there is sufficient evidence to support the claim that there is a linear correlation between overhead widths of seals from photographs and the weights of the seals. Okay. So that's that 8-step hypothesis testing procedure here. So you want to read the directions very carefully and regarding what they're asking for. Sometimes they may ask for the critical values here. Sometimes they may ask for the p-value. Okay. Of course, the p-value, you can get that from the TI 83 or 84 plus calculator. The critical value, you have to look at the number of paired data and the level of significance and use table A-6 for that. Okay, so that does conclude this video on section 10-1 that deals with correlation. Do feel free to email me if you have any questions about the homework in MyMathLab, or if you have any questions about any of the examples that were presented in this video.